Hello and welcome to this video tutorial. Today we're going to look at work and energy. We're going to be completing our notes for this entire unit. In this particular lesson, we're going to examine the concept of work, various forms of energy such as potential energy, kinetic energy, and even be able to look at going in between kinetic and potential energy within a problem called conservation of mechanical energy. We'll take a look at work-energy theorem, applying work to not only forces that are parallel to motion, but forces applied at angles as well. Please remember to pause or rewind the video as needed. Part 1, forms of energy. Well, let's begin with potential energy. There's actually several different kinds of potential energy. We can define potential energy as the energy that is stored by something due to its vertical position or due to its deformation or something. But it's the potential for some force to do work. Okay, so let's break down the different kinds of potential energy. We can begin with gravitational potential energy. Okay, we'll be writing the variable for it as PE sub G for gravitational potential energy. It depends on height. It depends how far off the ground an object can fall. And specifically, it is the potential for gravity to do work. So the higher an object is, the more work gravity will do if it actually falls. The equation for it is mass times g times height. The next kind of potential energy is the potential energy stored in a spring. So we can call this spring or elastic potential energy. And we're going to be abbreviating this PES for essentially spring potential energy. Okay, this is the energy stored in a spring. But specifically, it's the energy stored in a stretched or compressed spring. So the spring has to be deformed from its natural length. The equation that we use for it is 1/2 kx squared, where k is what's called the spring constant, relating how stiff the spring is. Okay, that's going to be in newtons per meter. And x is the stretch or compress length. Now, some other forms of energy that we'll encounter more conceptually would be, for instance, chemical potential energy, right? Batteries, for instance, store chemical potential energy in the chemical bonds that make up a particular compound. And when a chemical reaction takes place, some of the bonds are broken and some of that energy gets released. So batteries, for instance, convert for using the electrical, convert chemical potential energy to electrical potential energy, okay, which is our fourth. And we'll be dealing with electrical potential energy next semester when we begin studying electricity concepts. Okay, so I'm going to hold off on those two. Now, kinetic energy is the energy of motion. Okay, the equation we're going to use for it is Ke equals 1/2 mv squared, where you can see that the kinetic energy varies with the mass directly, but it varies with the velocity squared. Okay, now internal energy is something that deals with the motion of molecules. It relates to heat. Part 2, conservation of energy. Well, the law of conservation of energy, which I'm going to abbreviate LCOE, or just COE, is basically a statement that says that energy cannot be created nor destroyed. But it can change forms. It means the total amount of energy remains constant. If there is no unbalanced force, then specifically total mechanical energy, that means kinetic and potential. Okay, conservation of energy means all forms of energy, including thermal energy, sound energy, vibrational energy, things like that. But if there's no outside force, if there's no net force, for instance, friction, okay, if there's no friction acting on the system in any way, then the total mechanical energy remains constant. Okay, and we can kind of abbreviate it this way. Our equation for total energy is going to be E. So E is going to be total mechanical energy. And so if E is the total mechanical energy of the system, that means it's the sum of your kinetic and all of your potential energy. And we can summarize that by saying that the total energy at one point in the problem is going to be equal to the total energy at any other point in the problem. So in this first example, we get to apply conservation of mechanical energy right off the bat. Please note that you can establish zero potential energy anywhere you like in the problem. I tend to prefer putting it at the lowest point in the problem just because that makes sense to me anyway. But it's arbitrary. You can put zero potential energy anywhere. Now, what we'll do is we have a 100-kilogram roller coaster, starts from rest at the top of the hill. At the base of the hill, its speed is 24 meters per second part A, what was the height of that hill? And part B, what is the speed, or at what height, excuse me, will its speed be 12 meters per second? So if we kind of sketched out what this might look like, you're starting with a big hill like this, and it's coming down, and then there's some other height, right? Well, so we'll call this point A, where we're starting from, point B, the base of the hill, the bottom of the big hill, and then point C just kind of represents that height that you get to when you're 12 meters per second. Okay, so what we're going to do is we're going to start off specifically between point A and point B. Okay, and here's why. We have the speed at the base of the hill. That's 24 meters per second. We're trying to find the height of that hill. So one second. There we go. We're trying to find the height of that hill, and we can do that by using conservation energy to work backwards. Here's what we do. You start by establishing the energies at each point. The kinetic energy at point A would be 0 because we are told that the car starts from rest at the top of the hill. Okay, remember, let's go back to our previous set of notes here. Kinetic energy relates to the motion of the object. So if the object's not moving, it has no kinetic energy. But it does have potential energy to start. Okay, and that's we don't know what it is. So instead of writing question mark, what we'll do is we'll write the equation that matches that, which is the mgh. Now at the bottom of the hill, we do have kinetic energy at point B. So I'm going to write its equation, 1/2 mv squared, and potential energy at the base of the hill, I'm going to basically say it's 0 because it's the lowest point in the problem. All right. Okay, so for part A, we have initial total energy, which would be the energy at point A equals the energy at point B. And what we're going to do is we're going to go ahead, I'm going to highlight these points so you can see them. What is the total energy at point A? Well, it's just the potential energy right there. So you're going to replace EA with the potential energy at point A, which is mgh. Okay, now you do the same thing at B, right? What's the total energy at B? Well, it's just the kinetic energy at the bottom of that hill. So we're going to replace EB with 1/2 mv squared. So what you end up doing with conservation mechanical energy is you don't choose any equation like you once did in kinematics. Instead, you synthesize, you create the equation based upon the energies involved. Now, you're solving this for H. Okay. Now, you'll notice, even though the question gave you the mass, it really doesn't matter because mass is going to divide out of this particular equation. So it doesn't matter if it was a 100-kilogram roller coaster or 500 kilograms, the mass is irrelevant. Now let's go ahead and divide away G. Okay, and then go ahead and plug in. So H is equal to V squared over 2G. And I guess for now, I'll go ahead and use 9.8 for G. So we're going to go 24 squared divided by, what, 19.6? Okay, and so the original height of the hill is about 29.4 meters high. Okay, now it says at what speed, or when its speed, excuse me, is at 12 meters per second, at what height will it be when it gets to that point. And there's actually a bunch of different approaches that you could do to work this part of the problem. We could go from point B to point C, since we know the potential energy at point B is 0 and the kinetic energy is 1/2 mv squared. Or, and at point C, you do have height above the lowest point, so you do have potential energy at point C. So I'm going to write that mgHc to give it a subscript there. And then you do have some kinetic energy going over the top of that hill. So we're going to have 1/2 mv, 1/2 mv squared, bc squared. So I could go between those two, okay, as one potential source of the problem, where this is my initial energy, and that's equal to my total final energy, which is the sum of those two. Okay, that's one possible solution. Okay, so let me write that down. I'm going to work this actually two different ways so you can see the variety of approaches that can be done. So one possible equation, again, I'm going energy at B equals energy at C. So 1/2 mv, I guess, B squared equals 1/2 mv C squared plus mgh C. And then you're trying to solve that for HC, right? How high you have to be. Okay, one of the first things I'm going to do is I'm going to get rid of this term here, subtracting it over to the left. Okay, and we have 1/2 mvb squared minus 1/2 mvc squared equals mghc. And then you can see to solve for h, you just have to divide away the mg. And when you divide away the m, there's an m in each term. So mass is again going to cancel. Okay, and then g, right? G is going to be divided by each term. So this height, and if you look at what's common, we're basically going VB squared minus VC squared over, essentially, if you factor out a 1/2 G. Okay, so VB squared, we were going 24. So 24 squared minus 12 squared over 2 times 9.8. And you get about 22 meters in height for part B. Okay, so now just to kind of note and just sort of touch on this question, no, we could actually do the same problem, get the same solution if we went, let's say, from part A all the way to part C. Okay, let me show you above here how that would work out. Okay, so if we started with part A, the energy at part A is just mgh, but it's mgha, equals all the energy at C, which is mghc plus 1/2 mvc squared. And again, remember what you were solving for. You were solving for HC. So I'm going to subtract this term over to the left, divide out the m's. So I have mgha minus 1/2 mvc squared equals mghc. The masses will cancel. Divide by g. Okay, and you can see height C is going to be height A minus v squared over 2g. Now that's specifically vc squared. So what was height A? We found that to be, what, 29.4? Okay, and then we're going 12 squared over 2g. And you can see we come out with the exact same solution. So conservation of energy basically allows you to sort of work at any 2 points along the problem. You don't really care about what happens in between points in the problem. You just want basically bookend points. You want an initial part and a final part. And you essentially get to choose if provided you have enough information to establish what those energies are at those points in the problem. Part 3, work energy theorem, describes the idea that a net force or an outside force or an external force or whatever you want to phrase it, a net force caused a mass to accelerate. That's how we understood Newton's second law of motion. But now we can kind of phrase in a different way. A net force actually causes a change in energy. And we can state it as a net force results in net work done. So net work done on an object equals the change in energy. All right, let's see how the equation can be written. Work, which basically equals the parallel component of force, which is F cosine theta times distance. Now, the net component of force is equal to a change in energy. That's work energy theorem. Now, I write it as delta E because honestly, it could be the net work done to lift something. Okay, so for instance, you could really apply this a lot of different ways. Work could equal a change in potential energy. Okay, remember, if you're applying work, think about what you're doing. You're applying a force over a distance, right? Now, if you did work to lift something, what would you be doing? You would be changing an object's gravitational potential energy, right? So that's one way we could write it. Or let's say you were pushing something from rest. That means work could be resulting in an object's change in kinetic energy. Or maybe you were stretching a spring from its normal position. Work could equal the change in spring potential energy. So work energy theorem could really be applied in any of these instances. Okay. Again, the equation for work, let's kind of break this down. The equation for work is really a parallel component of force times distance. And if you draw a picture, you kind of see what we're talking about here. Let's say you have some force applied up at an angle like this. You have the components, F cosine theta is going in the same direction as the distance the object was moved. That is the parallel component of force. That is why this is written as F cosine theta times distance, or more frequently stated as force distance cosine theta. Okay, so that's the typical equation for work. Now, when an object is moving in the direction the force is applied, so say it's a horizontal force, well, cosine of theta would be 0. for a horizontal force because it's not, no angle above the horizontal. So cosine of 0 is actually 1. And so work equals force times distance for a parallel force. Work equals negative force times distance for an anti-parallel force, like friction. Okay, so for instance, when a force is going the same direction as an object's displacement, positive work was done. Okay, positive work in this case here. When the force is applied opposite to an object's displacement, negative work is done. And we can also use work energy theorem above to make sense of that. See, a parallel force is doing what? It's increasing the energy of that object. Increasing the energy corresponds to positive work being done. Whereas an anti-parallel force like friction is usually going to decrease, not usually, always going to decrease the energy of the object. Therefore, negative work is done. Now, again, you can also use the whole trigonometry approach too. The angle between force and distance for a parallel force situation is 0. Cosine of 0 is 1. So you get force times distance times 1, or just positive force times distance. Whereas an anti-parallel force, the angle between force and distance is 180 degrees, right? Cosine of 180 is negative 1, or force times distance times negative 1, or negative force times distance. So for example C, we have a 20 kilogram mass with an initial speed of 5 meters per second slides across a level rough surface. The coefficient of friction between the surface and the mass is 0.4. What will be the speed of the block after it has slid 2 meters? Well, let's draw a picture of that. You have your object here, and it was moving with an initial speed of 5 meters per second, and it's sliding, right, a distance of 2 meters. And I'm just drawing the dashed object to represent where it will be. And we want to find out what the final speed is when it reaches that point. Okay, so this is definitely a work energy theorem problem, and work energy theorem we're going to abbreviate as WT, work energy theorem. How do we know this? Because the work done by friction has reduced the energy of this box. Thus, the final speed is going to be less. So work is equal to, in this case, a change in kinetic energy, right? Or work is equal to kinetic energy final minus kinetic energy initial. Now you can break it, you should break it into this point into their respective equations. So for instance, work would be force times distance. And I'm leaving it as a generic force, but you're going to have to replace it with the actual force in a minute, is equal to 1/2 mb squared minus 1/2 mb naught squared. Now replace the fact that your force is a friction force. So friction force times distance is actually negative work done. So negative force times distance. Okay, and now that we have things mostly in place, okay, we don't have things entirely in place because we need to essentially put in the value for friction. Remind yourself, friction is equal to mu times normal force, and normal force in this case is going to balance the weight, so it's mu mg. So that would be 0.4 times 20 times 9.8. So I'm just going to run that quick calculation for the friction force. Okay, and so we're looking at about 78.4 newtons, and we'll use that. And recall, we're solving this for V final. So look at what we're going to do. We're going to start by taking this value here. We're going to add it over here. So we get a 1/2 mv naught squared minus friction times distance equals the 1/2 mv squared. Now, I have to get rid of, in order to get v by itself, I have to get rid of the 1/2, which I will do by multiplying by everything by 2. I have to get rid of the m, which I will do by dividing everything by m, and I have to get rid of that squared. So it's going to take me 3 steps to do this. Let's go ahead and start by multiplying each part by 2. And so I get mv naught squared minus 2 times friction times distance equals mv squared. Divide each by the mass. Now notice the mass cancels in this term, but not in that term. So be careful not to just automatically cancel it. And then last step, of course, is square root. So v, right, is equal to the square root of v naught squared minus 2 times the friction times the distance divided by the mass. So we're going to go 5 squared minus 2 times 78.4 times 2 meters divided by a mass of, I think it was 20. Yes. Plug that in. And we get roughly about 3.1 meters per second. Okay, in this next example, I guess we'll call it example D. I know there's nothing there, but go ahead and do it anyway. You've got a 20 Newton force used to pull a 2 kilogram mass across the level surface as shown. The coefficient of friction between the surface and the mass is 0.25. The mass starts from rest. Find the speed of the block after it has traveled a distance of 3 meters. Okay, so again, we do have a work energy theorem problem here, but this time it's the work done by this pulling force. The work done has increased the kinetic energy of the block from rest. And so we have force cosine theta times distance, that would be the work, equals 1/2 mv squared minus 1/2 mv naught squared, which is 0 because you start from rest. Okay, and we're looking for the speed of the block. So in this one, we are, again, solving for speed. So think about what your steps are going to be. You're going to have to multiply by 2. Let's rewrite this, and we get 2 force distance cosine theta. Notice I'm rearranging the equation there just to make it simpler to plug in. Cancels there, equals mv squared. Next step is what? Divide by the mass. Last step, square root. 2 times the force times the distance times the cosine of the angle divided by the mass. Now, coincidentally enough, those two will cancel, so that kind of makes it simplified to what, 20 times 3 or 60 cosine 3? And then square root that. We get roughly about 7.2 meters per second. Part 4, non-constant forces. Now, non-constant forces are usually dealt with in terms of what are called force distance diagrams. Okay, now something to consider, let's type this in together. The work is the area under a force versus distance graph. So let's take a look at this example. A 20 kilogram mass is pulled from rest along a frictionless horizontal surface by a force which increases as a function of distance as shown below. So you can see that the force is increasing from 0 to a value of 20 newtons, right, over 5 meters. So it's as it's getting farther, the force is getting stronger. So how much work is done by the mass? Well, here's how you do it. We're going to find the area underneath that. And so we can see that the area is going to be, work is going to be the area, which in this case, you can see it's a triangle, right? 1/2 base times height. Or 1/2, in this case, 5 times 20. Right, which would be 50 joules. Okay, so it's pretty simple to find work from a graph. What is the speed of the mass after it is covered a distance of 5 meters? Now for this one, we'll go ahead and use work energy theorem, because we have the amount of work done that did what? It sped up the mass, it increased the energy of the mass. So work equals, work is equal to a change in energy. So in this case, a change in kinetic energy. So work done is equal to a change in kinetic energy. Let's see, pulled from rest. So the initial kinetic energy was 0. So work is equal to initial kinetic or final kinetic energy minus initial kinetic energy, which is 0. And so the work done that you found, the 50 joules, is equal to 1/2 mv squared, and you're solving that for v. In which case, it's the same steps we've been doing, which is what? Multiply by 2, divide by mass, and square root. Right? So it's 2 times the work divided by the mass, or 2 times 50 over the mass, which was 20, right? And then don't forget to square root that. So 2 times 50, right, is 100, divided by 20 is 5, square root of 5 is a little more than 4, a little more than 2, excuse me, about 2.2 meters per second would be the speed of that object.